Here we have the electronic control panel, and the power to the lathe is turned on and off with this push button switch. You turn the lathe on by pressing the green button, and that turns on the AC power to the lathe, illuminates the tachometer digits, and pressing the red button turns the lathe off, turns off the AC power. Down below here you can see we have the speed control knob, and then we have this yellow LED, which is referred to as the fault light, and I'll explain later what that does. And this is just a pilot light or AC power indicator, so when the power is on, this green light comes on, but it's pretty dim, a little bit hard to see, but you can also tell the power is on by looking at the digits here. Now, this knob here controls the forward and reverse direction of the spindle, and the center position is neutral, so the spindle won't turn when it's in the zero or center position. And an interesting thing about the power switch to this lathe and many of the other lathes made by SIEG is that it has an internal relay, and the purpose of that is if power is interrupted to the lathe while you're working on it, for example, if you had a temporary power failure, a momentary power failure, or you had a circuit breaker pop in your home due to an overload, this the power switch will cut off, but when the power is restored, the lathe will not automatically restart. In order to restart it, you have to press the green on button. And that's a safety feature so that if you're working on the lathe and perhaps its spindle's rotating at high speed and the power goes out, you don't want the spindle to start up spinning again suddenly when you're not expecting it when the power is restored. So that's the purpose of that. And while we're on that subject, I recommend that you always have an emergency power fail lighting system of some sort in your shop. You can get inexpensive units to just plug into an outlet, because you don't want to be working on your lathe and due to a power failure or a circuit breaker popping, suddenly find yourself in complete darkness with the lathe still spinning. So it's happened to me before, and I learned my lesson once, and now I always keep power fail lighting in the shop. So let's take a more detailed look down here at the speed control knob. I've zoomed in here on the speed control knob so that you can see that the speed range is divided into a low range indicated by this L, which goes up to a maximum of 1200 RPM, and the high range, which goes up to a maximum of 2800 RPM. Now, this dual range is characteristic of what I call the classic style motor, which is a brush type DC motor, and it's been used on the mini lathe since the very early ones. It's improved over the years, but about 5 or 6 years ago, SIEG introduced another model of the lathe that has what is called a brushless DC motor. And the advantage of the brushless DC motor is that it has quite a lot more torque throughout the range, and because of that, instead of having two ranges, it's all in one range. Now, on the brush type motor that this lathe has, in order to get more torque in the low range, there's actually a set of gears in the headstock up in this area here, and there's a lever on the back side of the headstock that switches from high range to low range. So that's what these refer to. Whereas on the brushless motor lathes, there's no need for the high-low range at all, and so that lever is not on there, and there are no gears on the headstock. So that helps keep it a little quieter, and because it's direct drive from the motor to the spindle, you get more power applied directly. You don't have any losses in the gear train, nor do you have any noise from the gear train. So if you're going to be doing a lot of work on large diameter materials, 4, 5, 6 inches diameter, or you're going to be working in kind of a more or less production mode and want to take the heaviest cuts possible, then the brushless motor might be a better choice for you. On this lathe with the brush type motor, it's more than adequate for the majority of work anybody's going to do, but as you get up into larger diameter work, you will have to take lighter cuts than you would with the brushless motor. And again, on this type of lathe, 90% of your work is going to be done in the low range, and about the only time you really would use the high range is for polishing or perhaps drilling with a very small diameter drill bit, less than an 1/8 inch diameter. This yellow light here is called the fault light, or LED, and it indicates an unsafe operating condition which stops the lathe. One case where that can occur is if the lathe is operating. If you were to lift the safety shield over the chuck, you can see the lathe is immediately stopped. And if you then return the safety shield to the lowered position, the lathe does not restart, but the fault light illuminates. In order to reset the fault light, you have to turn the forward reverse switch to the 0 position, which turns it off, and then turning it back to the forward position, the lathe will resume operation. Another case where the safety light will illuminate is if you're taking too deep a cut. If you have say a 4 or 5 inch diameter workpiece here and you try to take a heavy cut and you overload the motor, the motor speed control will detect an excess current in the motor and it will stop the lathe and set the fault light. So in that case, that's a warning to you, or an indication that you're taking too deep a cut. You need to back off a little bit, reset the lathe, and then you can resume cutting at a lighter cutting force. Down here on the right side of the electronics control box is a fuse holder, and you rarely will blow a fuse on the modern lathes, but in the lathes made before around 2004 that did not have the internal overload protection built in, if you took too deep a cut, you'd most likely blow the fuse, so you had to keep half a dozen of them around the shop just in case. But with the overload protection built into the speed controller, you'll rarely blow a fuse. In fact, it's probably been 10 years or more since I've blown one. But nevertheless, it's a good idea to have a few spares on hand, and they're short level fuses, but you can find them inexpensively on eBay, and you may be able to find them at Radio Shack if you're lucky. I've opened up the electronics control panel so you can see what's around the back here, and I don't recommend that you do this at home because you don't want to risk getting any metal chips in here for what I hope are obvious reasons. But I thought it would be informative for you to see this. But the circuit board here controls the motor speed, and we have a series of MOSFETs with some heavy-duty heat sinks here, which send a pulse width modulation, or PWM, signal to the motor, and it maintains a specified RPM as set by the tachometer, and also maintains high torque. So as you try to slow the motor down, or you apply a load to the motor, the controller will automatically compensate to maintain a constant RPM. So that's a big advantage when you're taking heavy cuts. You don't lose torque as you might on some other types of motors, or not nearly as much in any case. But this is the on-off switch here, which, as I mentioned, has a relay built into it for power fail safety. And transformer, I guess, powers the LED display up here on the tachometer. And we have a sensor here for the RPM readout that measures, it's a magnetic probe, I believe, that measures the pulses from the motor spindle, or from the lathe spindle, and translate that into the RPM readings. So that's just wanted to give you that look in there. But the circuit board is pretty high quality. The newer ones are nicely made, and the older lathes back in 2000 and before that had what looked like hand-wired circuit boards with a lot of discrete components on them. And these newer ones are very, very nice, very clean and professional looking. So, and the reports that I've gotten are that they're a lot more reliable now than they used to be back in the bad old days, back around 2000 and the early 2000s and previous to that. So that's all good news. I'm about to remove the back panel here that covers up the motor, so we can take a look at the motor that drives this guy. And there it is. And it's labeled as 350 watt, which is what we expected. Now, on some of the other mini lathes made by SIEG, as well as others, you may find a 250 watt motor on some of the smaller ones, which ends about here. So this is a larger motor than you might find. So check the specifications for your vendor when you're going to select a machine, and see which type of motor it has as part of the criteria for making your decision. Now this one has a different arrangement, much better arrangement than in the old days. It's been a while since I've looked at the motor compartment on one of these mini lathes, but it has some adjusting screws and lock nuts here and here, and those are used for tensioning the drive belt. So to tighten the drive belt, you would loosen this screw down here and tighten the one here. And I guess they look like they're hex head bolts, which would make sense since they press against the housing of the motor. So that's your motor belt tension adjustment. And there's a hinged bar that runs through here. It's not really very visible. I don't think I can give you but it looks like the motor is attached to a bar that runs through this casting, and that acts as a hinge point for the motor. So it looks like a decent arrangement, and generally these belts don't stretch much, but you might have to, particularly after the first 3, 4, 5 months of running, you may experience a little bit of stretch in this belt, and if that happens and the lathe is under a heavy load, sometimes you can hear this belt skipping a notch or two, or a couple of notches, and if that occurs, then it's time to remove this back panel and adjust it. I don't know that there's any specific setting for this belt tension, but you just want it tight enough. This is set at the factory, and it's probably about right, and when you push it in with your finger, it shouldn't flex in more than maybe 1/8 of an inch or so at this point, so you'll have to use your own judgment on that. But if it's flexing, you know, 1/2 inch here, then that's too loose. While I've got the motor cover off, let me just make a comment here about the motor brushes. Now this lathe has the brush type motor, or what I like to call the classic style motor. The two high-end lathes have brushless motors, which are better in many respects but more expensive. But the brush type motors use a carbon brush that presses up. It's under spring tension or spring compression, and it presses up against a copper commutator inside the motor shaft, and over a period of time those brushes wear down gradually. They look kind of like a fat graphite pencil lead with a square cross section if you were to take it out, but I don't want to do that. But in any case, they do wear over time, but in the 15 years or so that I've been using mini lathes, I've never had to change or adjust a brush on the brush type motors, so it's unlikely you'll ever have to do that. But if you ever need to, this is one access point, and there's a hole here in the back panel to let you get at that. And there's a hole in the casting on the front side. There's another brush on the opposite side that you can get to from the front through an access hole. So something to know about, unlikely that you'll ever need to do anything about it. Alright, I've got what I hope will be a multi-part demo here. I wanted to show the digital tack in operation. And just a couple comments. These LEDs on all the lathes I've reviewed over the years do not show up well with digital cameras or video cameras, and they look a little washed out on the video, but in reality they're actually pretty sharp and bright and high contrast. And the actual color is sort of a deep cherry red, but at least on the video monitor I'm looking at, it looks like more of a pinkish color. So I've tried to adjust the lighting. The other problem is that the overhead lighting tends to wash out the numbers, and I have put a small piece of red cellophane over the display here to try to increase the contrast a little bit so we can see it better, and adjusted the lights so that they don't shine directly on the tack. So with all that set up, what I want to show here is that as I plunge the tool into the work, you should see the set speed on the tack drop down a little bit and then quickly recover to the original set speed. And I'll be taking a fairly deep cut here of about 40 thousandths, I think it is. Let me reset the tool here, and I'll go in one full turn of the cross feed, which is 40 thousandths on the dial, but that actually is going to remove 80 thousandths. So that's a pretty deep cut for a small lathe like this, and let's see what happens. Now, the other thing I might illustrate is if I take too deep a cut, I may stall the lathe, and in that case the motor should stop and the fault light should come on. So let's go up to about 600 RPM. Alright, and I'm going to use the power feed and see what happens. Well, Well, that was interesting. I started out here in this zone where I'd already removed some material, and went on in here to take an even deeper cut. So you can see these chips came off. That was a pretty aggressive cut. I didn't see this thing even blink down. I didn't hear the motor slow down or see the lathe slow down. So that's impressive. Let's try that again and see what happens. Let me get the camera repositioned here. Got all our pieces in place. I'm going to add another 10 thousandths here and see what that does. Well, once again, it didn't even slow it down. All right, I'm going to try and take a 1/10 of an inch off here. So I've set 50 thousandths on the dial, which should actually remove 0.100 approximately. And let's give that a try, see what happens. We'll go at 600 RPM. Okay, not a problem. Let's add another 10 thousandths, another 20 thousandths to the dial. We'll try that. Okay, it took that. Let's add another 20 and see what happens. So I'm adding 20 thousandths to the dial. I don't know what we're at now, but you can see these chips coming off here are pretty heavy duty. Okay, it was able to do that. I'm impressed. Let's take the tack, or not the tack, but let's take the dial caliper here, digital caliper, and measure the diameter. I measured it. The stock is nominally 875, but it's actually 878, just a little over 7/8 of an inch. And our finished diameter was 0.715. So we removed well over 1/10 of an inch, almost 2/10 of an inch, or somewhere close to that, and we might even be able to do 2/10 of an inch. That's pretty darn good for a small lathe like this. Now keep in mind, if we were using much larger diameter stock, you know, like 2-inch diameter or 3-inch diameter, the effective lever arm of the stock would impose a much higher load on the tool, and we probably couldn't take anywhere near that deep a cut. But still, for a lot of work, when you just need to remove metal quickly to get down to some desired diameter, it's nice to be able to just plow it off like that and get the job done quickly.